Howdy, this is Stefan, and this is another video on the MIPS Datapath. This is the second out of third videos. If you're looking for a more detailed explanation into the MIPS Datapath, I'd highly encourage you to check out my first video in which I do another example. So let's get started with this one. So we have a new function, a new instruction, sub m, where it subtracts the memory of RT from RS. Why is this new? Because MIPS instructions usually never perform arithmetic operations on memory blocks. You can perform arithmetic operations between register blocks, but the only time you access memory is during load word and store word. That is the significance of this this new instruction. So let's see what's happening. We have our register RS, which is being called, our register RT, which is being called, and RD is going to be written into. So as usual, we have RS going here. As usual, we have RT going in here. And we have RD, which goes into right register. Nothing fancy about that. So this, let me just label this RS, RT, and RD. Now, things get dicey when you get to the ALU. As you can see, we're subtracting the memory of RT from RS. So yes, we have RS here, but what we want here is the memory of RT. Let me write that down. The memory of RT. So that is what we want here. But the problem is we have just RT. We don't have the memory at the address given by RT. The memory is stored here. So we need a way to access that data memory and put it into the ALU. So what we're going to do is put in the address RT here. How we're going to do that is we're going to add a new multiplexer into which this is one of the inputs and RT is another input. Let me draw that out. So this is the value RT. And that is going into the multiplexer and into the address. So the address has the value stored in RT. So this is going to call the memory in RT. That is going to be outputted here. Now this is what we want in here. So we are going to take this out and bring in another multiplexer here into which this is one of the inputs and the read data is also one of the inputs. So the ALU result is going to be right here, RS minus memory at RT. So we have the ALU result here, which we're gonna send into our register destination, that is RD. So notice that we have added two multiplexers. Now the thing about a multiplexer is you can use them, but you have to also add another thing called the signal. So we want a signal to be there. So we're defining that the input for this multiplexer for RT is found at 1. So the signal should be 1 for this to go into the address. And we also define our multiplexer as the memory of RT being passed through the multiplexer. This being passed through the multiplexer at the signal value of 1. So both of these are defined at a signal value of 1. Now we have to define this signal. So we're gonna define a new control signal here called, let's call it sub m. Sub m. So whenever this is 1, this is also going to be 1, and this is also going to be 1. And therefore, the values which we want to go through the multiplexer are going to go through the multiplexer. So we're going to take sub m, and we are going to, now this is where it gets a little messy. I apologize for that. But this is going to go into this signal, and it's also going to go into this signal. So you get the gist that this control signal controls both these multiplexers. So what we want to do now is add a few control signals. For sub m, we know that this entire thing is not going to work if sub m is not equal to 1, because we need our signals to be 1 in order for sub m to work. So sub m equals 1. Register destination. What do we want our register destination to be? We want it to be 1. RD is passed when 1 is active. So register destination is 1. Are we going to branch? No, we're not going to branch at any time during sub m. So branch is 0. Are we going to be reading memory? Yes, we're going to be reading memory because memory is called from the address at data RT. So yes, we're going to be reading memory. So that is going to be 1. So memory to register, it asks the question, are we taking data from memory and directly taking it to register? The answer is no, we're not doing that. We're taking the ALU data and writing it to register. So memory to register would be 0. ALU opcode, what function are we doing in ALU? We're doing subtraction. So that, I believe, is 0, 1. Or if you have a different code for the ALU OPs, it would be whatever it is for subtraction. Memory write, that would be, we're not going to write into any memory, so that's going to be 0. ALU SRC, what are we choosing as a source? Honestly, we don't care, because whatever the source is, it's never going to get through. So because our S is equal to 1. So we're not going to care what this is. So it's going to be don't care. Register write. Are we going to write into register? Yes, we are. We're writing into RD. So register write would be 1. One caveat about this entire implementation, I guess it's a personal opinion as well, is that I don't like using this kind of implementation, mainly because it depends on the constrictions in your ALU. So if your ALU takes too long, you might extend beyond the single cycle and fall into the next cycle, which might mess up your entire system. So I would not recommend using this method if you're implementing this in labs. But theoretically, this should be okay as long as the time limit of the ALU fits well within your single cycle time. So that's how you do this problem, and that's how you fill in the control values.